So welcome to Electronics Excella. So we are in PYQ of signal systems of event semester 2024-25. So we'll see the remaining four number of 6 marks questions in this video. Okay. So let us check that. So first question is that how a signal can be reconstructed from in samples. Okay. So we are reconstructing the sample means we are doing the interpolations. Okay. From the sample signals, we will construct the analog signal. So let us check that. So the process of obtaining the x of t from the sample signal, that is st, is called the data reconstruction or interpolations. Okay. So that how that can be done. So this is our x sample signal, that is x of t into del t of t. This is the train of the input signal del t of t. So that can be written as summation of n is minus n plus infinity del of t minus of nt. Okay. That will be now this means del of t minus nt exists only for that t equal to nt, because the impulse signal exists only for del of 0. Okay, so that is why it exists only at t equal to nt. Okay? So let us put t equal to nt. So it will be x s of t equal to x into nt. And this one summation n equal to minus n plus nt del of t minus nt. Okay. So now we can use the reconstruction filter, that is assumed to be the linear and time variant, which is the unit impulse response, that is h of t. The reconstruction filter output y of t, that is given by convolution of x of st plus and s of t. So y of t equal to x s of t convolve with s of t. So you can see, you can put x s of t, that is this is the minus infinity plus infinity this x of nt summation of n is from minus infinity plus infinity del of tau minus nt h of means t minus tau into d tau. Okay, so this is the for means convolution formula. Okay, of xst and h of t. Okay, so next is your uh, so integral this x of nt, then integration minus infinity plus infinity. This is the same, I think, same I have written. Okay, we interchange the summation and integration part. So we can interchange the summation and integration parts. Okay. So now del of nt and tau minus nt exists only at tau equal to nt. Okay. So you can have y of t equal to summation of n is minus infinity plus infinity, then x of nt, then h of t minus of nt. Okay. Now there is a reconstruction filter. The sample signal xst is passed through a ideal low pass filter, whose bandwidth is greater than fm. The pass band is t and the filter output is x of t. So you can see the pass band. We can see is t. Okay. Then the filter is minus fs2 by 2 to fs by 2. Okay. So now the filter output is x of t. So let us check that. So the transfer function of this ideal reconstruction filter is h of f equal to t. You can say it is t for f mod is less than 0.5 fs. Okay. So the impulse response of the ideal reconstruction filter is, you can see, minus fs by 2 to fs by 2. Impulse, this is the impulse response. So t into this one e to the power j omega t into dx. Okay. So now you can see in place of omega we can write 2 pi f. Okay. So it will be, if we integrate this, okay, that will be this one. So e to the power j theta minus e to the minus j theta. Okay. You can write this in this way. So it will be e to the power j theta minus e to the minus by 2j. You can multiply 2j. So now it is a sine function, sine pi fst. So it can be written as sin pi fst. Okay. So now this sin pi fst, that can be h of t minus nt equal to sin pi of fs t minus nt. So you can put over here. So this is a sin pi fs t minus nt. So this is our y of t. Okay. So you can write this way also. Divide by you can see divide in this case. You can divide t over here. So it is t by t minus n. Okay. So this is how your means analog signal can be means reconstructed from the samples. Okay, where f is equal to 1 upon t. Okay. Now discuss the properties of autocorrelations. So autocorrelation, we know that it measures the similarity between the signal and its delayed version itself. So RXS tau equal to the same signal will be autocorrelated. If there is a same signal, that will be correlated, that will be the autocorrelation. So minus infinity plus infinity x of t minus tau d tau. Okay. So this is the first property. You can see it is the maximum at 0 level. So at tau equal to 0, you can see it is greater than RXS and tau. So it is maximum value we can obtain, absolute value we can obtain at RXS at 0. Okay, this is the property. Similarly, it is the even symmetry. Okay, that is the RXS tau equal to RXS minus tau. This is the function is symmetrical about the vertical axis. Okay, this is the properties of autocorrelation. Similarly, this is the mean square value. So at 0 lay, the autocorrelation output directly equal to the total of power or mean square value of the signal. This is called the mean square value. Okay. So this is a property, the boundary range, the normalized autocorrelation values falls between the -1 to +1. Okay. And this periodic signal, if the original signal is periodic, the autocorrelation function will be also the periodic at the exact same fundamental period. Okay. Next, the random noise delay. For purely random noise like white noise, the autocorrelation drops abruptly to 0 for any lag other than 0. Okay. So these are the properties of autocorrelations. Okay. Next one is your what is the discrete time processing of continuous time signal. So you can see this is the discrete time processing of continuous time signal. So we have an analog signal. So we have a pre-filter. Then the analog signal will pass through the pre-filter. Still it is analog signal. That analog signal will be converted to digital signal. Your discrete signal, it is x of n. Then that will be processed through the digital processor. The same signal is x of n. Then that will be processed to the DA converter to have the analog output. Then we have a pulse filter to get back to the signal. Okay. So this is our discrete time processing of continuous time signal. Okay. So we have a pre-filter. So it is an anti-aliasing filter. So we can see it ensures the bandwidth of the signal that is sampled is limited to a desired frequency range. Okay. So the signal should be band limited. Okay, that will be inserted by the pre-filter. Okay, it removes some additive noise or the other interferences which corrupt the desired signal. Then we have a AD converter that convert from analog signal into the digital signal. That AD converter is a combination of sampler, quantizer, and encoder. Okay. Then we have a digital processor. So it performs some basic operation on the digital signal to produce the output which is in the digital form. Then we have a DA converter. The DA converter performs the reverse operation of the ID converter. It takes the digital output from the processor and convert it into the analog form. The DA converter consists of quantizer and recorder. Okay. Last one is a force filter. The force filter is a low pass filter which is used to recover the message signal from the sample signals. Okay. So last question is that explain the process of aliasing or aliasing effect in signal processing with the need diagram. Okay. So you can see that it is a continuous time signal of x of t, which is the maximum frequency, it is omega m. So this is the means response of signal, that is x of t. Okay, this is the frequency response. This is omega is the frequency. So that is band limited to minus omega to omega. So that is the maximum frequency is omega m. Okay. So now for omega s is sampling frequency is greater than equal to twice fm, or fs is greater than twice fm. Okay. So in this case, what will happen is that here the amplitude is, you can see 1. Okay, the amplitude is 1. Okay. Now it is the spectral replicate the higher larger in this case. Okay, larger separation between the non-edge guard band, which makes the process of filtering much easier. So you, even if a non-ideal filter is used, that the original signal can be reconstructed actually. So this is the thing when omega is greater than equal to greater than twice of omega. So these are called the guard bands. You can see there is a gap, there is a larger separation between these two bands. These bands are called the guard bands. Okay. I have not written. So we can write GU, okay. GURAD, guard bands. Okay. So in this case, the original signal can be, we can get back the original signals, okay, without any disturbance. Okay. So without any signal loss, we can have the original signals. So you can see over here, in this case, omega is greater than twice of omega m. So this is our omega s. Okay. So these are the bands. Okay. You can see there is a 1 upon twice, because this will be equal to 1 by ts into this x of omega plus x of omega minus omega s, okay, plus x of omega minus twice of omega s, okay, plus x of, you can see, dot plus x of omega plus omega s, then we have x of omega minus twice omega s, okay. This is the spectrum of the sample signal, okay. So that is why there is a 1 upon ts. In this case, it is only 1 is there, okay. So this is the case when omega is greater than twice omega. So let us see when omega is equal to twice omega. In this case, there is no separation between the spectra. There is no Gaussian, you can see. So, but in this case also, x of omega can be obtained from x of sample values, okay, only by using the ideal low pass filter with sharp cutoff. So in this case, there is no Gaussian is there. So you can also you can get back the original signal from the sample signal, but using a ideal low pass filter. Okay, this is when omega is equal to twice of omega. So last case is there, omega is less than omega. So in this case, what will happen is that the low frequency component will overlap with the high frequency component omega, x of omega. That is why there is a distortion, and x of omega cannot be recovered, okay, from the sample values. So that is why distortion is known as aliasing. Okay. So let's check that you can see this, there is a overlapping of frequency component. Okay. Due to this, the original signal cannot be recovered, and we have a distortion that is known as aliasing. So this is called the aliasing. So aliasing will happen when omega s is less than twice of omega. Okay. So we can conclude that that is not overlap from omega s minus omega m equal to omega greater than equal to omega m. That is the, it's not overlap, and the original signal can be recovered from the sample signal. But in this case, when this is less than omega m, the frequency spectrum will overlap, and hence the original signal cannot be recovered from the sample signal. Okay. So for the signal recovery, omega s minus omega m is greater than equal to omega m. So omega s is greater than equal to twice fm. We can see fs is greater than equal to twice fm. In this case, the signal can be recovered. Or in this case, we can see this fs is twice fm is not a Nyquist rate also. Okay, this is called the Nyquist rate. Okay. So in realizing effect, it depends on the highest frequency components in the frequency component takes the identity of the lowest frequency component of the spectrum of the sample signal. So when fs is less than twice fm, the signal is undersampled and the frequency spectrum will overlap. So occurrence of aliasing, why it is occurs if the signal is not band limited to a finite range and the sampling rate is too low, means fs is less than twice fm. So how it can be avoided? That can be avoided by x of t, that can be made band limited, that can be assured by the using the anti-aliasing filter before the sampler, and fs should be greater than twice fm. Okay. So these are the last 6 mark questions. So these are our references. Okay. So if we have any doubt, you can free to ask in the comment section. Thank you all. Have a nice day. Okay. Thank you all.